Hi everybody, this is section 1.4, Properties of Radicals, for our Math 101 College Algebra class from our Hawkes Learning textbook. All right, so in this section we're going to talk about radicals, properties of radicals. First thing we're going to look at is the notation with radicals. And when you have a radical, and you start off, you're always going to look at, so like here, if I have the square root, or we'll start off, the square root of 25. We typically say our answer is 5. Now it could be -5. We're used to seeing this radical. Now it's a square root, and even though we don't see it there, we know that we have a 2 there. Just to review the parts of a radical, this little number right here is called the index. Okay. Then you have the radical sign, which is your check mark with a tail. So this is the sign, the radical sign. And then this is what we call the radicand. And what they are telling us here is, in this first case, if n is an even natural number, that means if we have an even index, like a square root, a fourth root, a sixth root, whatever it is, then the radicand, the number inside the radical, must be a positive number. So it has to be positive, like 2, 4, 6, anything. It could be an odd number, but it has to be a positive number inside that radical. So A has to be a non-negative real number. So it has to be a positive number underneath there. It could be a decimal, has to be just positive. And what they are saying here with this part right here is just like when we looked at the square root of 25 when we said the answer was 5. What they are saying is that 25 is equal to 5 to the second power. And that's what you're doing when you're finding the square root or the cubed root or the fourth root, the fifth root. You're really trying to find what is the root of the multiplication problem. What number can I multiply together twice if it's a square root to get the radicand? What number can I multiply together 3 times to find the cubed root of the radicand? Now our other case is if we have an odd index. So like if I'm looking at the cubed root of a number, or the fifth root of a number, or the seventh root of a number. If I have an odd index, then underneath my radical, I can have a positive or a negative number. Unlike with the square root where we have to have a positive number underneath here I can have a negative. The reason being, if I wanted to find, let's say for instance, I was going to try to find the square root of -25. Okay. Most of you would be like, oh, it's -5. But think, if I square -5, so if I go back up to this and I do -5 squared is equal to -25, is that true? If I square -5, I always get a positive number. So that's why underneath an even index, you have to have a positive radical because you can't have a negative under there. If you do, that's when we get into our complex or imaginary numbers, which we will talk about later. But let's say I wanted to find the cubed root of -8. I do know that I can multiply together -2 3 times, and that will give me -8, because -2 cubed is the same as -2 times -2 times -2, which 2 negatives here give me a +4, but 4 times -2 will give me a -8. So that makes my answer a negative. So what they're saying here on this slide is a lot of words, but if you have an even index, you need your radicand, the number underneath, needs to be positive. If you have an odd index, so the little number outside the radical, then your number inside the radical can be positive or negative. And here, this slide again just kind of goes over everything we talked about. It goes over and they talk about radical notation, how to write it with a radical sign. The number n is called your index. That's on the outside. A is your radicand and the radical sign. And again, with the square root, that's the only one we don't put the index in. If we see something like this, we know it's the square root. We know the index is a 2, but we don't always write it. Any other index you do have to write in. All right, so here what we are going to do is just find the answer to these radicals. The first one we're looking for is we have the 5th root of negative 32. So we need to find a number that we can multiply together 5 times. That will give us negative 32. Now, this one, again, we can use our calculator to find it. But something like the number 32, it's a very low number. So if it's low and you're multiplying a number together 5 times, I always say start off with 2. Now, it's negative 32, so I'm going to try, if I did negative 2 times negative 2 times negative 2 times negative 2 times negative 2. Negative 2 times negative 2 gives me 4. 4 times negative 2 will give me negative 8. And then I'll do negative 8 times negative 2, which gives me 16, times another negative 2, the final one, which will give me negative 32. So here our answer is negative 2. The 5th root of negative 32 is negative 2. And we could do that because our index was odd. It was a 5. Here, they want the 4th root of negative 16. Our index is even. So what's the one rule if you have an even index? You don't have, the answer is not a real number. It would be when we get into negative, or not negative, but complex numbers or imaginary numbers. So this answer would be not a real number. But for C, the problem looks very similar, except now the negative is on the outside. So to do that one, I can, because what they're really asking is, what's the 4th root of 16? And then take the opposite of it. I know that the 4th root of 16 is 2, because we found up here, if we did 4 times, we got a 16. And then they want the opposite of it. So in this case, my answer would be a negative 2. Because again, you evaluated the root first and then took the opposite. And then for our last one, the square root of 0. Well, what number can you multiply together twice to get 0? That would be 0. The square root or the cubed root of any of 0 is always 0. The next thing that we're going to look at, and you will have some classwork on to kind of help you get this, is to simplify a radical. And a radical, similar to like a fraction, they're not always in simplest form. You can remove some perfect cubes or squares. So in order for a radical to be in simplified form, the radicand must contain no factor with an exponent greater than or equal to the index of the radical. The radicand contains no fraction, so you don't want to have a fraction in your radicand. You want to rationalize that denominator. The denominator, if there is one, contains no radical. So, for instance, here, if I had something like the square root of 40. All right, it's a radical, it's not a perfect square. But sometimes they want you to keep the exact answer, which means they want you to keep it in radical form, but you do have to pull out any perfect squares that are in there. So what I do is I think of 40, and I think of my factors of 40. What can I multiply to get 40? So like 1 and 40, 2 and 20, 4 and 10, and then 5 and 8 will also give me 40. So here, what I'm looking for is I want to find a pair of factors that also has a perfect square. And this is where knowing those perfect squares will help you out. And when I say perfect squares, like 2 squared, we know like 2 squared is equal to 4. 3 squared is equal to 9. 4 squared is equal to 16. 5 squared is equal to 25, and so on. And when I'm looking here, I do see right away that I have 4 and 10. 4 is a perfect square. So I can take this radical and break it up. I can do the square root of 4 times the square root of 10. That square root of 4 becomes a 2. And my answer would be 2 square root 10 because we can't do anything with the 10. And this would give me an exact radical answer in simplified form rather than giving me a decimal equivalent if I use my calculator, which, again, because it's not a perfect square, will be a decimal that would never end and never terminate, so it would be irrational. We will look at more in later slides, and we'll look at some involving fractions and then also with variables as well. All right, and here, this is just saying when we're simplifying our radicals in this book and right now, we are going to assume that all expressions are defined and are real numbers. So they're not going to give us any like negative numbers underneath an even index radical. We are working everything, every variable we have, we are assuming is a real number. So, and we'll look at how to treat our answers. Sometimes if you have variables, we do need to use some absolute value symbols if we have that even index to show that your number is always going to be a positive number or a positive variable. All right, so here we're just looking at some different properties of radicals. Our first one says that if you have a radical, much like I just did the square root of 40, you can take a radical, like 40, I broke it down and made it the square root of 4 times the square root of 10. Or, like here, they have the cubed root of 3x to the 6, y to the second. So you can break it down into the multiplication of like radicals to that so that it's equivalent, and that will help you simplify it. For property 2, if you have division with a fraction in there, you can break it up into 2 separate radicals and then simplify those. And then if you have a radical within a radical, you can actually put it under one radical and just multiply those indexes together. And we're going to look at some problems and simplify them so you'll see some of these properties in action. All right, so the first thing we are going to do here is we are going to simplify the cubed root of negative 16 x to the 8th y to the 4th. The first thing I'm going to do, just to help us out a little bit, is I'm going to break it down to the cubed root of negative 16 times the cubed root of x to the 8th, and then the cubed root of y to the 4th. So we can look at each factor individually. Now, you will see, I'm going to solve it one way. The book may show you a little bit differently, but all ways are comparable. You'll get to the same answer. And that is one of the nice things about math is you can solve things multiple ways and still get the same answer in the end. So it's good to look at all different viewpoints and choose the one that works the best for you. Here, so the cubed root of negative 16. It is not a perfect cube, but if I think about my cubes here, I know that 2 to the third power is 8, and 3 to the third power is 27. Well, 27 is too big for negative 16, so I'm going to look at the cubed root of 8. And I know for negative 16 that I could do the cubed root of negative 8 times the cubed root of 2. The cubed root of negative 8 would be negative 2, and because it's a perfect cube, it comes out of the radical. And then we still have our cubed root of 2, which is not a perfect problem, so it will leave it where it is. Next, we are going to be looking at the cubed root of x to the 8th power. Now, when you're dealing with your variables, what you want to do here is you want to just go ahead, and what I do is I divide. So we're going to divide 3 into 8. We're basically going to see how many perfect cubes can we pull out of that 8. So I can do the cubed root of x to the third times the cubed root of x to the third times the cubed root of x to the second. So this problem right here, cubed root of x to the third, that would simplify to an x. This would simplify to an x, the second one. And then this one we can't do anything with. So right now our answer that we have is -2. Then I have x times x, so x squared times the cubed root of, I'm going to erase this little x so I have space, the cubed root of x, or 2, it came from here, and then my x squared we'll put there. Now, another way to do that, instead of breaking it down into these each time, is divide. 3 goes into 8. So if I divide 3, divide, not radical, but 3 into 8. 3 goes into 8 2 whole times, and then the remainder is 2. So that whole number here becomes my exponent for the x's I'm bringing out. I'm bringing out 2 x's. The remainder is what stays underneath the radical. We can take a look and do that right here with this one. So 3, I know, goes into 4 1 whole time. And we subtract, and we have a remainder of 1. So when I go to write my final answer here, I am going to have, I'm going to put it over here, -2x squared, and then 3 goes into y 1 whole time, so I'll have a y. And then I'm going to have the cubed root of 2x squared, and then remember we have 1y left over. So my final answer for the first one will be this. All right, next we are going to look at the square root of 8x, or 8z to the 6th power. And we are going to solve it. Here, remember, I'm going to break it down. I'm going to do the square root of 8 times the square root of z to the 6th power. And the square root of 8, I know I can break it down to the square root of 4 times the square root of 2. And the square root of 4 is a perfect square, so that becomes 2 square root 2. Now, z to the 6th, again, do your division. 2 goes into 6. It goes in evenly. So if I divide 2 into 6, it goes in evenly 3 times, and there's a remainder of 0. So that means that what's going to happen is this, if I take the square root of z to the 6th, it is equal to z to the 3rd. There's no radical left. Now, when I do write my answer to this, because we are assuming that we are dealing with real numbers and we always have positive answers, any variable, when you have an even index, so like 2 or 4, any variables that you get, you want to put absolute value signs around those variables when you pull stuff out. So I'm going to do 2z to the 3rd in absolute value symbols times the square root of 2. And again, this just shows that that z variable, it's always going to be a positive number or a radicand underneath the radical. And when you pull it out and you have that even index, you need to put the absolute value symbols around it so that they know you're dealing with positive numbers. And this only happens when you have that even index and an odd variable there. All right, let's take a look at C as well. And now this one, what you want to do first is, because it is a fraction, you want to break it up. So we're going to look at it first as the cubed root of 72x squared over the cubed root of y cubed. Now the nice thing about this one for the denominator is the cubed root of y cubed. 3 goes into 3 1 whole time, so my answer there is going to be a y. Now we do need to break up the top part, and the cubed root of 72 I know that I can break that up into the cubed root of 8 times the cubed root of 9 times the cubed root of x squared. And then the cubed root of 8 is going to be the whole number 2. And then we're going to have the cubed root of 9, which we can't do anything with. And the cubed root of x squared we also can't do anything with, so we'll leave it underneath that radical. And that's going to be all over y. And that will be all the simplifying we can do. We can't do any more simplifying, so we are done with that one. All right, and here, just a word of caution when we're working with radical expressions. One thing to remember is that even though if we have a problem like we did earlier, the square root of 40, and I could break that down into 2 factors. So I could do the square root of 4 times the square root of 10. And that worked to simplify it. With addition, it's different. You cannot break it down. If you have the square root of 5 plus 7, it is not the same thing as the square root of 5 plus the square root of 7. This one you can add underneath and make it the square root of 12. Here, I cannot add these radicals because they are not the same number underneath. It's kind of like combining like terms. Think of it as the same variable. So this problem, the square root of 5 plus 7, all under one radical, is different, and you would get a different answer if you tried it on your calculator than the square root of 5 plus the square root of 7. So just remember those two are totally separate, and you can't break up an addition problem underneath a radical. All right, so here we are going to be simplifying radical expressions. And really what we are doing here is we are rationalizing our denominator. If you recall, you cannot have a radical in your denominator, so we need to get rid of the radicals in the denominator by rationalizing our denominator. For a, the first thing we're going to do is break it up. So we are going to turn it into the 5th root of -4. So we're going to do the 5th root of -4x to the 6th over the 5th root of 8y squared. And now what we need to do to rationalize our denominator here is we need to turn our denominator into a perfect 5th root so that we can get rid of that radical underneath. It's almost like writing an equivalent fraction. So what we need to do is, what I'm going to do is I need to find a way to break this down. Now the book, how they show you how to do it, is they take it and instead of writing 8, we know that 2 to the 3rd power equals 8. So what they do is they write it, okay, let's write it with an exponent. And then in order to get all the way to 2 to the 5th power, or a perfect 5th root, then they're going to say, well, I need to add to that 2 to the 2nd power. And then we have our y squared. And to get it to a perfect 5th root, they want to turn it into y to the 5th power, so we're going to have to times it by y to the 3rd. Now, what that means is whatever we do to the bottom, we have to do to the top. So I'm going to keep my -4x to the 6th power, and then I'm going to add times it by 2 to the 2nd and y to the 3rd, because that's what I added to the bottom of my radical. When I go to simplify this, right now I'm going to have the 5th root of, we are going to have here -4 times 2 to the 2nd is 4. So I'm going to have -16, and then we would have x to the 6th power, y to the 3rd power. Excuse me. And then on the bottom, I'm going to have the 5th root of, and I'm going to leave it in power form right now just to show you. We would have 2 to the 5th power, because remember when you multiply powers with the same base, you add your exponents, and y to the 5th power. So when I go to simplify that, on the top, negative 16, there's really nothing I can pull out of that. Other than I could pull out that negative sign, make it a positive 16, just pull out like a negative 1. Because negative 1 to the 5th root of negative 1 is negative 1. And then x to the 6th, I know 5 will go into 6 one whole time. So I'm going to pull out a negative x, and then I will have the 5th root of 16. I have one x left over. I pulled out a group of 5. And then y to the 3rd, I can't do anything because 5 won't go into it. And then on the bottom, the 5th root of 2 to the 5th power is just going to be 2. And the 5th root of y to the 5th power will just be y. So that would be our first one with our denominators simplified or rationalized so we get rid of the radical underneath. Now, I do want to show you one real quick. If I were to just have like a square root, they're a little easier to deal with. If I just have something like, we'll do 7 over the square root of 5. I'm going to make it 7 square root 2 to show you with a radical on the top. All right, now to get rid of this, to rationalize our denominator, it's already broken up to 2, but because it's a square root, it's a little bit easier. All I have to do is multiply by my radical on the bottom. So I multiply the square root of 5 times the square root of 5. That will give me a 5 on the bottom. Now, whatever I do to the bottom, I have to do to the top. So on the top, when you multiply radicals underneath the radical, you multiply those two together. So I would keep the 7, and then we're going to have the square root of 2 times the square root of 5, which will give me the square root of 10. And if I needed to, I would simplify that, but it's not simplifiable. So I would leave it like this. So square roots are a little bit easier. All right, next, we're going to take a look at b. So here we're going to simplify b. Now, to rationalize this denominator, it's a little bit different than the first one because to rationalize it, we have an expression down here on the bottom. We have the square root of 7 plus the square root of 3. And in order to rationalize our denominator when you have a math problem, like an addition or a subtraction problem, what you need to do is you need to rationalize the denominator by multiplying by the conjugate. So you're going to multiply by the conjugate. All right, so the conjugate is simply, you take the expression, and instead of doing square root of 7 plus the square root of 3, you multiply it by the square root of 7 minus the square root of 3. So all you do is you keep the two terms and change the addition sign. If it's addition in the first one, you make it subtraction. If it's subtraction here, then you make it addition here. And again, whatever you do to the bottom, you have to also do to the top. So we'll do that as well. Now, on the top, I would leave it 4 times the square root of 7 minus the square root of 3 right now because it's already factored, so it makes it easier to simplify. And then what we're going to do on the bottom is multiply. We'll FOIL. So the square root of 7 times the square root of 7. When I multiply that, I'm going to put it up here, the square root of 7 times the square root of 7. If I multiply it together, I'm going to get the square root of 49, which simplifies to the whole number 7. Anytime you multiply two square roots together that are exactly the same under the radical, you get whatever's under that radical out of it. So I'm going to put my 7 there. And then I'm going to do 7 times negative square root 3. So that's going to give me negative square root 21. And then I'll do square root of 3 times the square root of 7. So that'll be positive square root 21. And then the square root of 3 times the negative square root of 3 will give me negative. Again, remember, whatever you have under that radical, if it's the same, you get out of it. It's going to be a negative 3. Now, the nice thing here is when we're simplifying, negative square root 21 and positive square root 21, they cancel out. So we get rid of radicals underneath, which is what we want. And then I just have 7 minus 3. So that is going to give me a 4. And then on the top, I have 4 times the square root of 7 minus the square root of 3. And then we can do some simplifying because 4 and 4 are both factors here. They will cancel out. They equal a 1. So I can simplify that fraction. And then my answer is the square root of 7 minus the square root of 3 for that one. All right, so now we're going to look at C. And C, again, is going to be just like B, where we have a multiplication problem here. Or not a multiplication problem, we have an addition or subtraction problem. So to get rid of that expression, we need to use our conjugate. Excuse me. So what I'm going to do is I'm going to multiply everything by the conjugate of 5 minus the square root of x. So my conjugate, remember, you keep the same two factors and just change the sign. So this is minus, so I'll make it plus. So I'll do times 5 plus the square root of x. And whatever you do to the bottom, you have to do to the top. Okay, so then I'm going to move it up here so we have some space. On the top, again, I'm going to leave it as it is for right now, because it just makes life a little bit easier. So we have negative square root 5x times 5 plus the square root of x. And then on the bottom, when we multiply, 5 times 5 is 25. 5 times the square root of x would be plus 5 square root x, because they're a whole number and a radical, you just put them together. And then in the middle, you should notice we'll have minus 5 square root x. And then the negative square root of x times the positive square root of x. Again, remember, if it's the same thing under the radical and you're multiplying two radicals square roots together, you get whatever's under the radical, so it's going to be minus x. And then we can simplify here. Now, again, like before, those middle terms, you have positive 5 square root x and negative 5 square root x. So they can cancel. And then on the bottom, right now, we have 25 plus x. Now, we don't want a radical on the bottom, but a variable is okay. So this expression is okay, as it is. And then on the top, we have this negative square root of 5x times 5 plus the square root of x. And we could distribute here, but honestly, it's not going to do anything to help us simplify. So we're just going to leave it as is. Sometimes if you distribute, you can do a little like factoring and simplify, but this is factored form. It's not going to help us do anything. So we are done. All right, so next we are going to look at rational number exponents. So now we're going to look at what do we do if we have a fraction for an exponent, or if we have a radical and we need to work with it, but maybe we can't work with it in radical form, what can we convert it to? And in that case, we can convert it to a power with an exponent that's going to be a fraction. So if I have something like the square root of 7, remember, we know, even though we don't see it, that we have a 2 in there. That is equivalent to, as a power, 7 to the 1/2 power. The 1 comes from the exponent of the 7, which if there's nothing there, it's a 1. The 2 is the index in your radical. So if I were looking at like the cubed root of x to the 4th power, if I were to write that in power form, it would be x, and then my fraction would be always your power of your radicand is your numerator, so 4, and the index is always the denominator. And we're going to look at converting some of those, and then also why we would need to do this and how to simplify it. One other important thing to look at here is, when we're working with radicals, we can switch to the powers, which is why we're looking at it, because sometimes it's easier to simplify that way. But also, just a reminder, if you have a negative exponent, in order to make that a positive, we don't like dealing with the negative exponents unless we're looking at something like scientific notation. So to change that, if you have a negative exponent, remember, you take the reciprocal to make it positive. So if I had something like 6 to the negative second power, if I wanted to make that into a positive exponent, I take the reciprocal of this. So I made it into a fraction by putting a 1 underneath, and I would flip it and make it 1 over 6 to the second power. So again, to make it a positive, you take the reciprocal. If you have something like, if I had 5 to the negative 3/2 power, again, to make that positive, turn it into a fraction, and then flip it. So it will be 1 over 5 to the 3/2 power. And once you flip it, that negative sign on the exponent goes away. It makes it positive. All right, so here we are going to simplify the expressions and write our answer in the same notation as the original expression. So here we have 27 to the negative 2/3 power. Right now, as it is, it's a little hard to solve with that fraction there, but we can turn it into a radical in this case and solve it much easier. So what I'm going to do is convert it from a power to a radical. So remember, the big number is your radicand. Oh, and the first thing I want to do before I do that, ignore the negative sign there, I want to turn it into a positive exponent. So I am going to put a 1 underneath of it and write it as 1 over 27 to the 2/3 power. Now that I have it positive, I'm going to convert it into a radical. So the 27 goes inside the parentheses. The 2 is the power on the 27, and the 3 is my index. Now, what I'm going to do is, you can write it one of two ways. You can write it like this, and then simplify from there. But that is going to require a calculator, because I don't know 27 to the second power off my top of my head. Or we can rewrite it so it looks like this. 1 over the cubed root of 27. And then you can always put parentheses and put that exponent on the outside, because then it's easier to take the cubed root of 27, which I know 3 times 3 is 9, 9 times 3 is 27. So I know that the cubed root of 27 is 3. And then I will square it using my 2. And so my final answer here is going to be 1/9. So by converting it to a power, it was much easier to solve. And sometimes that's easier than typing into the calculator, looking at it like that. And yeah, I do want you to know how to do both and use the calculator or use writing it as a radical form. So like on your quiz, when you show your work, I do want you to send me the work of you actually converting it to a power and showing me how you solved it. For B, and let's see, that's in, it was exponent form. There's no more exponents, so this is our final answer here. For B, right now I really can't do any simplifying with this as a radical. But the nice thing is, if I convert it into a power, I would have, now this is my radicand, it's negative, it's not the exponent, so I'm going to have negative 8, I'll put that in parentheses, to the, now the exponent on my 8 is a 1. So it's negative 8 to the 1/9 power times, now x is another factor, and that's going to be to the 6/9 power. Okay. Now what I need to do here is, really when it's written like this, I can't do any more simplifying. But what I can do, my 6/9, I know that I can simplify that by 3, so I can make it 2/3. And my negative 8, and this is where you have to kind of be a math detective and figure out, well, what can I do? How can I fix this? I can rewrite that negative 8 as, I can make it negative 2 to the 3rd power. And then remember, if I have an exponent times like a power times an exponent, you multiply. So I would multiply the 3 times the 1/9. So now I'm going to have -2 to the 3/9 power times x to the 2/3 power. And what I can do here is that -2 to the 3/9 power, I can simplify that. I can make it -2, divide them both by 3 to the 1/3 power, and I have x to the 2/3 power. Which you're probably like, well, those fractions aren't the same, doesn't help us out much. But it does, because we've simplified it as much as we can. Our denominators are the same, which means my power for my radical would be the same. So now we're looking at the cubed root of -2, and my power here is a 1, so I don't need to put it, and then x to the 2nd power. So we took this radical here, which looked like, there's nothing we can do to simplify it. But by putting it in exponential form and looking at the powers, we were able to simplify it down to the cubed root of -2x². I know you guys think that's really awesome and cool. If we were in class right now, we'd be having a party. All right, so we're going to take a look at our next 2 examples. And the first thing we're going to do is simplify the 4th root of x². Now, as we have been simplifying, right now we can't do anything with it to simplify. But if I turn it into a power, so I rewrite it as x to the 2/4 power, I can do some simplifying there. My x to the 2/4, I can simplify that 2/4 and make it x to the 1/2 power. And then they would probably want it written back in the same form that it was, so it was radical form. So now what I can do is, here, because I am working with an even exponent or an even index, we do want to throw in some absolute value there because my power is even. So what we're going to do is when we put it back in radical form, to show that our x has to be a positive number, we'll put the square root of x, and that's our answer. And remember, the 2 is your index. You can write it, you don't have to. The 1 is the exponent, we don't have to put it in there. So that is A. Now, when we look at B, first thing we want to do is, right now, we can't multiply radicals unless they have the same index, and these do not. But what we can do is we can turn them into fractions or powers with fraction exponents. So I would have 2 to the 1/3 power times 3 to the 1/2 power. Now, right now, when I look at that, just make that 1/3 a little better. Okay. Normally, what I would do is I would add my exponents and simplify, but my bases are different. In order to add your exponents, the bases have to be the same. So right now, I don't have much to help me with. But what I can do is, in order to write it as a single radical, I have to have the same denominator, and I don't. But I can create equivalent fractions. I'm going to pretend like I'm adding those fractions together. And what I'm going to do is create denominators for these fractions that are exactly the same. So for 3 and 2, I know my common denominator would be 6. So now, if I convert this fraction to a 6, I had to multiply the 3 times 2. So remember, you do the same thing to the top. So I'll multiply the 1 times 2. So I'm going to rewrite it as 2 to the 2/6 power times, and then I'm going to do my 3. I'm going to convert that to a 6, which I had to do 2 times 3. So I'll do 3 here, and I have the 3/6 power. The 3/6 power. Now that I have the same exponent, that is wonderful. But what I want to do here is I'm going to go ahead and convert it back to radical form. And again, in the book, they may do it a little bit differently. Depends on what you're looking at. But in the end, you'll get the same answer. It's just sometimes my steps might vary a little bit from the book, but look at both, see which way you like better, and use that way. Now that I have the same denominator, I can convert it into a radical. So I have the 6th root of 2 to the 2nd power times 3 to the 3rd power. Now what I'm going to do is underneath that radical, because that's all under one radical, I can simplify that. So now I have the 6th root of 2 to the 2nd is 4, and 3 to the 3rd is 27. And then the last thing I'm going to do is just multiply the 4 times the 27, so I will end up with the 6th root, 108. So we took this problem here that seemed like, there's nothing we can do with that. We really can't make it into one single radical, but by turning it into powers and using those fractions as exponents, we were able to convert it into one single radical. So again, I know you're thinking this is super cool. I'm so excited to be taking this class and learning this stuff, and I am so glad you're here. If you were in the classroom by now, you would have learned that I am a little crazy. I do love math, and I love showing you how cool it is. So hopefully, you'll walk away with this and say, wow, I have a really cool teacher, not, oh my gosh, she's crazy, she likes math. That is it for 1-4, and up next will be section 1-8.